Hello and welcome again. In this video, we'll talk about another attack on the ElGamal signature. And this is going to be similar to the one we did for the RSA. And it actually has the same name. It's called the Existential forgery attack. Now, so what I mentioned was that this is similar to the RSA signature attack. And in the sense that the attacker can actually generate a valid signature. In this case, the signature for the ElGamal is a pair of numbers R and S that come with the message. And of course, the message that is being sent is kind of random in the sense that the attacker cannot really control the semantics of that message. So let's look at what the attack is. So let's look here at the attack. So I have a diagram here. So the attacker, as always in our case, we call our attacker Eve. And Eve is the one that's going to produce a valid signature with the public key from Bob. So Eve is going to use P, alpha, and B. That's the public key. And she's going to produce a message and a valid signature that is going to be sent to Alice. So Alice will actually check that, and it's actually going to be a valid signature. So let's look at the procedure here. So it's in 3 steps. So the first one is that Eve here is going to select 2 integers, and she has control over that. So she can select 2 integers between 2 and p minus 2, including those 2 numbers. And at least one of them has to have no common factors with p minus 1. That is the condition that is here, that the GCD here between j and p minus 1 is 1. So at least one of them have no common factors with p minus 1. I made a little mistake there. It's supposed to be GCD. Now, once the Eve has that selection, she's going to compute the signature now. So the signature is going to be computed like this. It's going to be alpha to the I, and that's information that Eve has because she knows alpha. B to the J is another thing that she knows, and this is going to be all modulo P. So that's part of the signature, that's R. And the S part of the signature is going to be negative R that multiplies the inverse of J modulo p minus 1. That's why we needed the GCD between j and p minus 1 equal to 1, so in such a way that the inverse of j here will exist. So as you can see here, she already computed R and S, and this is going to be a valid signature for a message that now she's going to produce. Now, she doesn't have actually much control over what the message is, but the point of this is that she's going to generate a valid signature, even though the message might not make any sense. So the message here will be just S multiplied by I, and this is modulo P minus 1. And so she's going to take all this information, the message M and the signature RS, and she's going to send that through the insecure channel. And you will see in a second, when Alice goes ahead and checks this, then this is going to be a valid signature for the ElGamal signature. Now, this is a lot more involving that the existential attack that we did for the RSA has more steps and kind of like, well, it's complicated. It doesn't look like this is going to be actually something that is going to work. But I'll try to prove to you. So this video is not going to have actually an example because what I want to do is I want to actually show you that this actually works. And so to show you that this actually works, this procedure here, I will kind of have to give you a proof for it. So this is going to be a video where we're going to do a little bit of a proof actually. So let's read this in here. So if Alice applies the verification algorithm, which is the one that she has to apply, then the output will be true, meaning that the signature will be valid. Now remember that the verification algorithm has only the output is always true or false. Now let's recall what is the verification algorithm. So the verification algorithm is these 2 steps, and actually it's simple. So we compute this variable t, which is not really necessary to compute it. Just compute this right hand side that we have here is b to the r times r to the s modulo p. So we compute that, and then we compare this one to alpha to the message. And if those 2 things happen to be the same, modulo p, then that means that we have a valid signature, and then otherwise we don't have a valid signature. So we actually have to do this computation here. Now, we don't have actually specific numbers. So what I'm going to do is I'm going to take all this information that is here and show you that it doesn't matter what kind of numbers are being chosen here, as long as you make this requirement, then you always gonna get a valid signature for the ElGamal scheme. Okay, so let's go ahead and do the kind of proof that I was talking about. So let's compute T. That's the first thing that Alice will do. So this is on the side of Alice, and let's check that it's actually working. So what is T? T is congruent to b to the r times r to the s modulo p. Why is this true? Well, because that's the verification algorithm. That's what Alice will do to do the verification. And then we'll compare this to alpha to the message, and then if they're the same modulo p, then done. The signature is valid. Now, so let's start putting down some equations. So this is equation number 1. This is the one that Alice computes. Now, this equation number 2 that I have here, that's r equals to the alpha to the I times beta to the j modulo p. That's what Eve constructs. So these are the things that Eve is doing. Let me scroll back all the way up here again and show you that that's exactly what it is. That's the r that you see over here. This one's the r. All right. So that's what Eve has here. Now, I'm going to combine these equations 1 and 2. So basically what I'm going to do is I'm going to replace the r that is here in this equation number 1 by this one. And I can actually do that because this is congruent. So this here is supposed to be symbol for congruence there. All right. So if I do that, which I can do because this is all modulo p, so I can replace this r by alpha to the I, beta to the j, which is exactly this expression that I have here. It's exactly that's number 1, replacing that over here. So I have b to the r, alpha to the I, b to the j, all to the s. And if, of course, if I apply the rules of exponentiation, which are also true in modular arithmetic, then I can have alpha to the I s times b to the j s. So it's all here. This is basically this step is just algebra. And then you can go ahead and do this. B to the r, b to the js, you can put them together in one single expression. You just have to add the exponents. So then I have alpha to the is, which is this one here, and b to the r plus js, which is this part over here. What I'm going to do is I'm going to call this last equation, I'm going to call that number 3. And we will refer to this one later. So this is actually true. This is true, combining the verification algorithm and the values that Eve chose for the attack. Now, this is also something that we know. This that S is congruent to minus R times J to the, or the inverse of J modulo P minus 1. This is also something we know because that's how Eve chose her values for the signature. That's the part that she did. Now, I'm going to use this equation 3 later, but let's unravel what this actually means. Okay, so what I'm going to do here is from this modular equality, I'm going to multiply by j on both sides. So if I multiply by j on both sides, then here the j is going to cancel. I'm going to have js congruent to negative r modulo p minus 1. Just multiply by the value of j here. And so I get this one. Now, after that, what I can do is I can add r on both sides of this equation here. So if I add r on both sides, then I get r plus js congruent to 0 modulo p minus 1. Now, what does this mean? This means that p minus 1 divides r plus js. That's the definition of modularity. Or another way to say it is that this guy, r plus js, is a multiple of p minus 1. And that's exactly what I have here. So this means that r plus js is a multiple of p minus 1. So I can write down r plus js equals to k. What k here is some integer. It's not a key or anything. It's just an integer. And that multiplies p minus 1, which is translating this fact that is here, this congruence. So now if I do that, I can write the following thing. I'm going to concentrate on now on this part of the congruence. What is this b to the r plus js all modulo p? And I'm going to look at that in the light of now this equality that I have here. So what is b to the r plus js? Now I'm going to replace r plus js by what it is equal to a multiple of p minus 1. So I say just b to the k times p minus 1. And I'm going to use properties of exponents. So what I can do here is actually just say, okay, this expression that is here is exactly the same as b to the p minus 1 all to the k. That's modulo p. That's the laws of exponents, which are also true in modular exponentiations. And I'm going to use a theorem that we have used several times, I think. That's called the Fermat's theorem. And the Fermat's theorem says that a number to the p minus 1 is always congruent to 1 modulo p as long as the GCD, or the greatest common divisor between the number and p is 1, which in this case it is. B to the p minus 1 doesn't have any common factors with, or b doesn't have any common factors with p here, because what is b? Remember, b is a power of alpha, and alpha is a generator, so they don't have any common factors. So I can replace this guy here by 1, so I get 1 to the k, and 1 to the k is, of course, 1, because it's 1 times 1 times 1, k times. So then what I have here is, if you follow this congruence here, what I have done is that b to the r plus js is congruent to 1 modulo p. I'm going to call this equation number 4. This one that is here. Now, this is all approved. So if you want to go ahead and read and go back and do it again, so that would be a good idea, because this is all kind of very involving. Okay, so now what I'm going to do is I'm going to replace 4 into 3. So I'm going to basically combine these equation number 4 into equation number 3. Now, keep in mind what this equation is, and I'm going to scroll up and show you equation number 3 again. And this is equation number 3. So I just to show you that this guy here is 1 modulo p. So I can replace this b to the r plus js by 1. So that means that t will be equal to, or will be congruent to alpha to the I times s. And this is all modulo p. And that's exactly what combining 3 and 4 will do. So then what I have here is that t is equal to alpha to the is times 1. And we're almost done. So you will see actually that this t will be congruent to alpha to the m modulo p. And that means that then the signature is valid. Okay, so to do the last step, actually, let's use what Eve also did. What Eve did was she computed the message m, and the message m was congruent to I times s modulo p minus 1. Now, I'm going to use the Fermat's not this last theorem, the Fermat's theorem, little theorem again. And Fermat's theorem says basically the following thing. If you have two elements that are congruent to p minus 1, congruent to each other, modulo p minus 1, they are congruent if you take alpha, or any number that doesn't have any common factors with p, to alpha to this element is going to be congruent to alpha to that element modulo p minus 1. The argument is very similar to the one I just gave you before. Now, I decided to skip a little bit of steps here, but the idea is you're going to use Fermat's theorem again from this step to here. You can do the following thing. If you want to do the steps, you're going to say m minus I times s is congruent to 0, and then m minus is will be a multiple of p minus 1, and you will apply Fermat's theorem there, and you will see you will get this. Now, you can see now more or less why that the conclusion follows. If you look at equation 5 and equation 6, t is congruent to alpha to the is, but alpha to the is is congruent to alpha to the m. So if you combine those two, 5 and 6, you will arrive to the conclusion that t is congruent to alpha to the m modulo p. And that is exactly the fact that says that the signature is valid. So the conclusion here will be that the signature is valid, which is not a very desirable thing to have, even though if the attacker doesn't have any much control over the message, she can produce a valid signature if she wanted to. This is for the school book ElGamal signature. So as I mentioned, this was just a video about a proof. Now in the next video, what I'm gonna do is I'm gonna give you an example on specific values that Eve will choose to produce a valid signature, and you will see that that's gonna work. And of course it's gonna work because this always works, because this is what we did in this video was the proof. So I'll stop the video now and I will see you in the next video.